Welcome to A2 Data Representation. At AS level, you built programs using basic integers, strings, and one-dimensional arrays. But real-world software is infinitely more complex. This unit gives you the professional tools to model custom systems, manage computer memory directly, organize massive disk files, and handle binary fractions with absolute precision. This is a heavy theory unit for Paper 3 and the absolute foundation for your Paper 4 practicals. We start by building our own custom data types. Instead of relying on standard strings where a typo can crash your system, you will create enumerated types. These define a strict, restricted vocabulary, like the specific days of the week or the exact states of a traffic light. You will also learn to implement mathematical sets using arrays, allowing you to perform unions and intersections. These structures prevent bugs and force your code to mirror reality.
Next, we look under the hood at how memory actually works. Pointer variables do not store data. They store exact memory addresses. As you can see here, instead of a rigid static array, you will use pointers to dynamically allocate memory while your program runs, linking individual pieces of data together into flexible chains. This is the silent workhorse behind dynamic structures like linked lists and trees, heavily tested in your exam.
Data is useless if it vanishes when the power cuts, so you must master how records are organized permanently on disk. We will cover serial files, where records are simply appended chronologically, making them perfect for temporary transaction logs. Then we step up to sequential files, where data is strictly sorted by a primary key. You will learn the exact algorithms used to update these sorted master files during heavy batch processing, like calculating a monthly payroll.
Sequential searching is far too slow for a massive database. To get instant retrieval, you will learn to design random access files using hashing algorithms. A hash function takes a key, calculates a specific disk address, and jumps straight to it without reading anything else. Crucially, you will also learn how to resolve collisions, which happen when two completely different keys accidentally generate the exact same memory address.
Finally, we tackle how computers store real numbers using the mantissa and exponent model for floating-point binary. You will learn how to normalize these numbers. Normalization shifts the binary bits to remove redundant leading zeros, ensuring maximum precision for a given number of bits and preventing wasted space. This process is highly mechanical, and mastering it will secure you 3 to 5 marks per calculation in your final paper.
By the end of this unit, you will have the architecture needed for advanced software design. You will be able to model complex systems with custom types, manage memory dynamically, retrieve disk data instantly, and calculate binary precision flawlessly. Take your time with the theory, practice the algorithms, and let us get started.